Okay, so I guess it's time to start. So hi, welcome to my presentation. I'm Michal Privoznik. I work for Red Hat like for 4 years now. I'm one of the main libvirt developers there, but I also work on other projects as well. Today I'm going to talk about libvirt, what benefits does it provide, what does it do on the top of QEMU. So basically QEMU developers have more insight into that. So QEMU KVM is really perfect hypervisor. I mean, it really is quick emulation, as its name suggests. It runs quickly, and it scales nicely. You can easily run dozens of virtual machines on a single desktop. Yeah, this is mainly due to lazy memory allocation or kernel same-page merging or whatever. But the point is, you can do that, and it's portable. When I'm developing libvirt, I usually run QEMU on my Raspberry Pi. So it runs everywhere and it runs everything. However, it has some disadvantages that mostly falls out of its scope. But if you want to use it in enterprise environment, you need to address them. So the first one is QEMU does not provide any host management system. So for instance, if you want to pass through an PCI device, you need to detach it and reset and do all kinds of stuff yourself. Then QEMU has just too many interfaces to talk to. For instance, you have this QEMU command line, you have the monitor, you have guest agent monitor. And if you want to use, if you are developing an application and you want to use QEMU in that, you certainly just, want to start up a virtual machine and don't want to bother really with talking to the monitor or, guest agent or something like that. QEMU, moreover, does not provide any language bindings, which again might be a disadvantage. And it doesn't really provide any intra-VM perspective, meaning you can easily start two virtual machines over the same read-write disk, and the file system corruption is then likely to occur. So this is the point where libvirt comes in. So libvirt is a standard C library, although we have bindings to other major languages out there, like Python, Perl, Ruby, Java, whatever, you name it. And we do provide a stable API. So whenever you are developing an application, you can focus on what's interesting for your application instead of chasing changing hypervisors or latest advices from them and stuff like that. libvirt is not only about QEMU, although I would say QEMU is our most intense developed driver. Driver is basically a backend that implements an API. The list of supported hypervisors contains Zen in all its flavors, like the Bear Zen, Zen API, libzen, and stuff like that. We do support VirtualBox, Linux containers, user mode Linux, believe it or not, and many others. I think the best way to show you what libvirt does is to walk you through a process of starting a virtual machine where all the interesting work takes place. So even before we query QEMU capabilities, libvirt will generate all the missing paths for you and prepare all the files that you need. For instance, if you are using an UEFI to your domain, it usually comes in two separate files. The first one is a file containing the firmware itself, and the second one is a variable store for the UEFI. While the first can be shared among multiple domains, the variable storage file, you probably want to have a per domain. That means libvirt needs to copy the file from master variable store file or whatever. And I should mention that at several stages of the process, user hook scripts are run or called. The hook scripts are basically user-written scripts to address host, to prepare host environment where libvirt has no support yet. For instance, they can signal their own application or something like that. So the first thing that libvirt does is we query a QEMU capabilities. We start up this bare QEMU process just to have a monitor to talk to. And we query several monitor commands to get list of supported devices, device attributes, command line arguments, and stuff like that. And this is one of the points I would really like to stress out. It's crucial for libvirt to know all this kind of stuff. So whenever you guys add a new feature, please make sure it's introspectable so libvirt can make decisions later, as we will see. Then libvirt will prepare the host devices for you. Basically, it will check whether the PCI device you want to pass through is not taken by already running domain. You certainly don't want to just rip off a PCI device from running domain and give it to another. Although some devices can be shared among domains like SCSI devices. Then we try to find an unused port on the host, unless you've specified port for VNC or SPICE in your domain configuration. Even though QEMU has this capability, we implement that ourselves because we need to report the port back to upper layers. So we can't rely on QEMU in that. This is basically done by binding to unused ports in the host, and we keep ourselves bounded to the port until the time comes and QEMU is executed. Then, unless you've specified NUMA binding in the domain XML, we try to consult NUMAD for the best placement, although this is somewhat mystery because the vCPU count or memory can be hot plugged, and so it can change during the domain's lifetime. Then we try to build a command line. This is the point where the majority of the host resources are pre-allocated. For instance, we create tab devices, by opening a tune device. We keep the file descriptor so that can be passed to the QEMU later. We plug the interface into the correct bridge. We set up network bandwidth limiting and stuff like that. Then the big times come, and we do the fork. To enhance security, we drop all the unneeded capabilities. So because the child will later become a QEMU process, so we drop all the capabilities that it's not going to need. For instance, one of the capabilities that we might preserve is the raw I/O capability to bypass the cache in the kernel, in the host kernel. So, because we want the child to be demonized, we need to do double forking. Therefore, we need to report the child speed back to the daemon. Child speed is needed because we need it in creating a CGroup, so we can make sure that the emulator is placed into the correct CGroup. Then the child will lock the domain disks. Historically, we were using a senlock for that, but we were not so happy with it, so we've created our own implementation to which we refer as virlogd. Virlogd has one major advantage because it keeps track which process has locked the disk, which bit has locked the disk. Therefore, whenever a QEMU process crash or just die unexpectedly, virlogd can make sure that no locked disk is left behind. Then we try to basically honor the NUMA settings by calling all the NUMA underscore something functions so that the child will be placed onto the correct NUMA nodes and allocate memory only from the configured nodes. And again, to enhance security, we drop the rest of the capabilities because currently we were needing like sysadmin capability. We changed the working directory and stuff like that. So once the child has done that, the daemon will create a bare CGroup hierarchy, which I will cover in the next slide. Basically, in the CGroup, we selectively allow only the devices that QEMU is going to touch. We use all kinds of CGroups. Basically, CGroups are a way of refining how kernel views the resources. For instance, in the block IO CGroup, you can limit the bandwidth that QEMU is able to read or do IOs from or to disk. Then we can use memory CGroup to cap the maximal amount of memory available to QEMU, and many other CGroups. For instance, CPU set, so that the child will run only on set CPUs and stuff like that. Since the daemon is now the only process running as root because child has already relabeled itself, the daemon will set the security labels on all the resources needed for the domain, namely, disk, character devices, sockets. If you are booting a kernel directly, then even the kernel image and all kinds of stuff. Once this is complete, we send a signal to the child, meaning child, okay, you can now execute the QEMU binary. And the daemon will then try to connect to the QEMU monitor to finish the runtime settings. For instance, one of the runtime settings that we set is disk passphrases, VNC or SPICE passwords. Even we try to query some information, for instance, the vCPU thread IDs, IO thread ID, and others. Up till now, the QEMU is started with domain CPUs paused, because you certainly don't want to have domain already running while you are setting the passphrases. So we unpause the domain CPUs and we run the post-exec hook script, which is called from other places as well. But yeah, so this one of the things that we learned the hard way was that there's always be a cost on using nested C groups. even though the kernel guys had made a great job in there, but there's still some price. So in the first example, you can see the old CGroup layout that we've used. Underneath is the new CGroup layout, so you can see we've saved like 3 levels of depth, which is great, basically. While doing this, we've managed to integrate a systemd in libvirt. So basically, systemd will do the CGroup layout setting for us. The idea behind there is to have one manager to set up CGroups. And while doing this, we've invented this new approach that, for instance, if you have an enterprise system running, you have enterprise VMs running there, but you have some test machines on the system as well. And if you limit the test machines per each domain, it may work, but you certainly want to limit the whole group of the test machines. And this is something which was introduced there as well. So in systemd world, a single domain is referred to as a scope, whereas a group of machines is referred to as a slice. So you can set, you can limit the whole group of virtual machines, and the group membership is then again configured in the domain XML. So this is the basic layout, that we create. This is example basically. You can see a virtual machine running here. Yeah, we need to do the name escaping for some systemd madness that I'm not going into. And you can see a slice called engineering here, running basically two virtual machines. If I were to run another virtual machine under the engineering slice, it will go, somewhere over here. And this is the layout that will be created per each CGroup that you've configured. Memory, device, CPU set, and all kinds of CGroups. So if you've created a virtual machine, that's nice. You can, with libvirt, you can start up a virtual machine, you can tear them down. But do you want to have your virtual machines to have a connectivity? One of the approaches in libvirt is to use so-called virtual networks, where libvirt will create and manage a virtual bridge for you and plug the domain interfaces into the bridge. The other approach is to, do the direct host interface pass-through into the guest, or, just to use make vtap, or to use Open vSwitch, and others. The virtual networks, however, have this advantage that we can run a DHCP server for you, which is basically a DNS mask binary. But virtual networks can work in 3 modes. The first one is network address translation, where the virtual machines will have their own address space, but share the host connectivity. They can work in isolated mode, where virtual machines will see only another virtual machines, but not the outside of the host. Or they can work in routed mode, where the virtual machines will share the address space of the host. So once you have a network to your virtual machines, you may want to limit what packets can they send. Ideally, this would be set by the guests themselves, but the problem is you can't trust the guest. Therefore, the rules, the network rules, must be applied from the host, and libvirt is able to do that. In this example, we are using a filter called clean traffic, and we are passing a variable with this value into the filter. And once the filter is evaluated, the variable will get its value, will be replaced with its value. And this is basically done on per VNIC basis. So it's important as well. Network filters, this is an example of the actual filter. Network filters form, sort of a chain or a tree similar to those in a BSD packet filter. So, the evaluation of a packet starts at the root chain and goes to child chains, and a chain basically can either accept packet, drop it, reject it, or return the evaluation process back to the parent. And this is important to note. This is the place where the variable will be replaced with its value once the filter is evaluated, which happens when the domain is starting up. I should mention that some variables are special variables in libvirt. For instance, namely IP variable, if not specified in the domain XML, which we've seen on the previous slide, libvirt will try to guess the IP address of the host and replace the value. There are basically two approaches when implemented in libvirt, how to guess the IP address of the guest. The first one is that libvirt basically listens for the DHCP communication between the guest and the server, so it can see whether a guest has been assigned more than one IP address, and these IP addresses then can be enabled in the filter. This is very strong rule when used combined, with filtering of untrusted DHCP servers that might be running on malicious guests in your network, on your host. The other approach is to listen for the first packet that the guest sends out, and the source IP address of the guest of this packet is taken as a guest's IP address. So that way we can allow only a single IP address on the interface. When I was talking about how libvirt starts up a machine, I've told that we do provide passphrases to your QCOW disk. This is something what we refer to as secrets in libvirt. You can use them to store passphrases for not just only QCOW, but for other disks as well. Basically, secrets, once you provide us a passphrase to the libvirt, we will provide it later to the authentication mechanism, and secrets can be viewed basically in two axes. The first one is whether a secret can be stored on the disk, or should be stored in memory only. The other axis is whether a secret can be shared with other entities in the system or is private to the libvirt, and libvirt will never ever tell it to anybody else. Speaking of the storage, libvirt even provides a way to manage your storage for the virtual machines. It's basically divided into two groups. The pools are basically a quantity of storage dedicated to the virtual machines, and volumes are then abstraction of physical partitions, and both of these can be divided into two subgroups. The first one is, a local, and the other one is shared. So, for instance, if you have a directory, a pool, then it's local with files in the directory as its volumes, or you can have a volume group, LVM volume group, as a pool with logical volumes as its volumes, or you can have a disk and with partitions and stuff like that. One of the interesting points here is that libvirt is able to build this for you if you provide us an XML. So, for instance, we can even partition your disk if you tell us to. One of the major points when doing virtualization is previously, before the virtualization, discussion and access control was enough because systems were typically physically separated. But nowadays, you often have, several domains running on the same system, and usually running under the same user as well. So, if a guest gets compromised, it is a threat to other domains as well, and potentially the host system too. So, one of the aims here is to have a policy enforced by the host kernel, so that even domains running under the same user cannot really harm each other. And this is where Linux comes handy. When starting the domain, libvirt will basically generate a Linux label for you and relabel all the resources the domain is going to need. So that way, if a guest gets compromised, even though it is running under the same user, it has a different Linux label, therefore it can't touch the other processes running under the same user. So Snapshots has been closely, pretty good viewed by Adam before me. I don't know, where's Adam? So I don't go into any much details. I'd say that in libvirt it is possible to basically do snapshot of a disk only, or do a memory only snapshot, or combine these together so you get a checkpoint. And the other axis is whether a snapshot is an internal, which means it is kept in the QCOW file, or it is external, which means it's a new file is created over the existing disk. So basically, creating an internal disk snapshot, it is somewhat possible to do in libvirt, but you don't want to do that on a running domain, because basically it represents a state of a disk on unexpected power loss, because the data held in the memory are not stored in the disk. Doing a memory snapshot basically boils down into a migration to a file, and doing checkpoints is supported both internal and external. Again, with libvirt, you can do all kinds of stuff over these snapshots. You can create them, revert, merge, and even delete. One of the main points here is that libvirt tries to keep the metadata to preserve an ABI stability. So if you revert to an older snapshot, the ABI of the host is preserved. And that brings me to the end of my presentation. I think the majority of libvirt developers are here. So if you wanna, ask some questions, just invite us to a beer. But you can ask questions now as well. Yeah?
Yeah. In the initial part of the presentation, you told that libvirt is bound to ports. Now my question is, if I want to do two tasks simultaneously, suppose I want to get status of a particular device or something continuously, and also I want to issue another libvirt API. Is it possible?
Yeah. So the question basically was whether it is possible to start a guest post, so you can do other APIs on the guest until the time you unpause it. Yeah, the answer is it is possible. If you are starting a virtual machine, it's done by an API which have flags, so you can specify, start this guest only in post state, so libvirt won't unpause the CPUs, and you can issue the APIs you want, and then issue the API that will unpause the guest.
Is it possible to issue two APIs simultaneously?
Yeah. Yeah. Any other questions? Yeah, Lane?
This isn't a question, but just more of a statement. Earlier you said that when QEMU developers are adding new features, it's very important that it be introspectable.
Yeah.
So that libvirt can query QEMU to find out whether or not that feature exists.
Yeah.
Because if the only way to find out that a feature doesn't exist is to try it and then have it fail, then that's no good.
Yeah.
The other thing, though, that's important, and I don't remember the last time I ran into this, but there was something that this was an issue with. It's also very important for anything on the QEMU command line that takes a file as an argument, that should also be able to be specified as an open file descriptor.
Exactly.
Because libvirt is running a group with full privileges, but it's running QEMU as an unprivileged process for security reasons. And if QEMU needs access to a file, it won't be able to open that file probably.
Yeah.
So what libvirt does for files like that, libvirt will open the file, pass the file descriptor to QEMU, and then QEMU, which is unprivileged, can operate on it. So that's also just another thing for any new QEMU feature that uses a file, make sure that it can be passed as a file descriptor.
Exactly. This is actually one of the points where I see a big gap. For instance, when I was talking about, binding ourselves to a unused port, so that can be passed to the QEMU later, it would be really great if we can just pass an open socket, because it's still racy. Even though we open a port, unused port, we have to unbound from the port once we are doing an execute of the QEMU binary, and this is the window where another process may come in and bind the port. So it would be really great if we could just pass an open socket for the QEMU. And even though what Lane said, it would be great if we could pass basically everything that is needed as a file descriptor or something. We are doing that already with tab devices, but I guess.
Yeah, a while back, I remember there was a discussion about making a generic facility in QEMU where you could open a file descriptor, give it a name, and send that as the argument for any file name on the QEMU command line. I don't know what happened to that. I lost.
Yeah. Any other questions, comments? Yep. No, okay. So I think that's it then. Thank you.